Hey folks, welcome back again to Advent of Code in F#. We're at day 23 part 2 and I left off part 1 with a bit of a bug actually. I was getting the wrong answer for the second part, but turns out that I had a bug in my longest path algorithm. I'm not gonna bore you with where it actually was, but the gist of it was that I was not always stopping my search at the finish line. So I had random paths that did not end up in the finish node, and I was counting those paths as like valid finishes, and that's not good. So I fixed that bug, and then I ran my longest path algorithm as it was for part 1, and then it turned out it would have taken me lots of CPU cycles and lots of years of patience. So that wasn't really cool. And then I did a couple of things. One was optimize my algorithm even more, where I changed my... I think I changed my graph representation. Let me do a quick look here. Did I actually? Yeah, I changed my graph representation from... the grid was like the 2D matrix containing the forests and the paths and finding neighbors. I had to take a look at all 4 neighbors and what was in there. I changed that representation to something called an adjacency list, I think. Is that the scientific term? Let me take a quick look here. Graph representations. There's multiple ways of representing a graph with its nodes and edges. Let's grab the first one. We were using... Actually, none of those. We were not using a adjacency matrix. We were just using a 2D matrix containing the nodes, and we were looking up the edges on the fly, basically. But for my part 2 refactor, I used this representation of a graph, which is an adjacency list. And if you take a look at the example here, this is a graph with nodes 0, 1, and 2, and vertices between them. Sorry, that was an undirected graph. This is a directed example. And this representation maps every node to a list of reachable vertices. So for example, it maps node 1 to vertices 0 and 2. And that's exactly what I did for part 2. So if you take a look at my part 2, I have something called a neighbor map. And a neighbor map is a 2D array. That's just a data structure to quickly access the adjacency list of the row and a column. So that's just to have instant access and not have to look it up in a map that's logarithmic. So that's why it's a 2D array. And that at that location, so for example, the start location, that's, what is it? 1, 0, 0, 1, 1, 1, 1, I don't know, but the start location contains a list of reachable nodes. And that was not enough either. My algorithm was still pretty slow. And then I introduced something that has to do with this cost. So my adjacency list does not contain all my direct neighbors, but all my interesting near neighbors, which might not be just next to me. It's a roundabout way to say that I compressed my graphs. So if you take a look at my code here, I'm going to go over detail in a second, but you see here, like, I do something called grid.compact, and that is actually compressing my graph, because let's take a look at the graph in the example and our own graph. Well, let's maybe take our own graph. Maybe I can show it better in a big graph. Yeah, so we start right here in the top left corner. And if you take a look at the path we take, there's only one path we can take for a while. So we can go downward, go right a bunch of stuff, go down, go left again, down, 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 right, up. So it's a very long path where there's no actual choices to be made. It's one directional, just go with the flow. And if you see that in a graph, you can actually make a more concise representation of it. You can get rid of all those uninteresting nodes in between. So for this example, it's the same thing. We go da 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 da, and this one is actually the first node in the path where you have a choice. We can go right or we can go down. So actually, if you take a look at the adjacency list for the start thing, this is not an interesting near neighbor. This neither. This is the first near neighbor on this path where something interesting happens. So this is the first and the only node in my adjacency list for the start node. And the only thing that changes is the distance. So the distance isn't 1 anymore. It's, I don't know, 1, 2, 3, 4, 5, 6, 7, 8, something like 15. So that's why you see in my code this neighbor map thing. It has a cost, and this cost is like the distance to that interesting near neighbor. And once I did all those things, so I reworked my graph representation to use adjacency lists, and I compressed my graphs, or I compacted them to get rid of the uninteresting nodes in between. Then my algorithm for my longest path would run in, I think, 40 seconds on the input, which still is not great by a long shot, but at least it ended below a minute, and I'm a happy camper. I spent way too much time on part 2, but I learned a lot. I had not heard about compressing graphs, and I did not know that graph representation could matter that much for performance. So yeah, I learned a lot about graph searches. And most important thing I learned actually is if you write it yourself, like we did, the chance for bugs, or the probability for introducing a bug like we had at the end of the last video is very high, very high. So I'm going to go over the entire code. But now we know the big ideas of what changed compared to part 1. So as I said, I introduced the cost because edges are not 1 by default anymore, because I can take 15 steps before I encounter an interesting neighbor. We're still in the 2D plane, and the neighbor map, that's the adjacency list as I discussed. Everything else is the same, so we have our next and next cells functions as we did in part 1. And I think this is part of the compacting algorithm. Yeah, it's part of the compacting algorithm. So let's maybe take a quick look at how I am compacting my graph. This is the compact function. I take in as an argument interesting nodes, but that's just a way of saying, hey, don't forget about the start and the end nodes. I really want those in this map as well. So that's what those already interesting nodes are. And then I just figure out all the nodes that have like more than 2 entry points. That's all the interesting nodes, and all the rest are boring on a path without choice. So I first find all interesting nodes with more than 2 incoming cells. So that's what you see here. If you do next cells for that location, you should have more than 2 neighbors that are reachable. And those, and my start and my finish, those are all the nodes I want in my compacted graph. So that's what this nodes variable on line 101 means here. And then I just build the adjacency list with distances using this distances2 function. And if you have that, I just convert it to a 2D array for faster accessing. So it's not logarithmic, but constant access if I know the row and the column index for a cell. So that's pretty basic. Let's take a look at distances2. How do I calculate for one node all the reachable nodes and the distance to those nodes? Again, it's using the next cells thing. So this is a bit similar to our search algorithm, actually. When I was writing this, I was encountering like, oh, now I need to do a visited set. So this is actually a search algorithm, but I'm using it to compact my graph or to build up distances to reachable nodes. So that was an interesting observation. But as you can see, if I want the distances to a set of nodes from a starting node, how I do it is I take a look at the next cells. I also do the visited thing as we did in our algorithm for part 1. And then I find everything that every interesting node that we just encountered, and this is like a step we took, but we did not find any interesting node. That's what I mean with misses. And hits are like, okay, we definitely found something interesting, so we definitely have something for the result set. And for our misses, we do like a recursive step, so we increase our path length by 1, and we go 1 deeper recursively for those misses. And if we know the hits stuff and the misses stuff, we know all the reachable, interesting nodes. So that's a very fast, very high-level explanation of how I built my adjacency list. And if I have my adjacency list, this is the longest path algorithm, as you saw, which takes this new adjacency list, and for the rest, it's the bug-free version of what we had for part 1. So it's a pattern match on the queue. If the queue is empty, we have our maximum path in the accumulating value, and otherwise we just visit the next element in our queue for the depth first algorithm, and we continue on. So this is very similar to part 1, but there were some bugs in there that are now removed. So yeah, actually I did exactly what I was going to do for part 1, which is what you see here. Replace every slope with a clear path and then just go. But the interesting twist was compacting my graphs and using a different representation, which is our adjacency list representation. So not as fast as algorithm, but I'm very happy with the results, and I will not be spending any more time on this. So this is it for day 23. Day 23. Lovely puzzle. Learned a lot. I hope you did too, and I hope to see you again for more Advent of Code in F#. Bye bye.